Advancing Financial Risk Management, a transparent framework for effective fraud detection. Financial fraud significantly undermines market stability by deceiving the stakeholders and concealing actual financial risks through the manipulation of income, assets, or liabilities, in addition to causing substantial losses to investors and heightening the risk of future stock market crashes. Financial fraud disrupts resource allocation and impedes the growth of the securities market. Consequently, financial fraud serves as a key catalyst for financial risk. As fraud tactics become more sophisticated, involving coordinated manipulation of financial statements, traditional detection methods often fall short. Early studies primarily relied on statistical approaches for fraud detection, introduced the M-score model and a numerical indicator to assess the likelihood of financial fraud. With the rise of machine learning, advanced models such as neural networks, decision trees, and support vector machines have substantially improved the accuracy of fraud detection. For instance, employee machine learning meta classifiers to detect financial fraud, achieving a significant improvement in prediction accuracy over traditional statistical methods. Recently, hybrid models have garnered increasing attention in financial fraud detection. For example, proposing an integrated machine learning framework to predict financial fraud, yielding promising detection results. Despite this advancement, however, most machine learning based models suffer from a lack of interpretability, which remains a key limitation and hampers their practical application and broader adoption. Feature selection remains a crucial aspect of fraud detection, with previous research emphasizing the significance of financial indicators in identifying fraudulent activities. In 1966, Beaver conducted pioneering work applying the predictive power of financial indicators in empirical studies to detect financial fraud. As machine learning models continue to evolve in the field of fraud detection, increasing attention has been given to feature selection to enhance model performance. Utilizing feature selection techniques to preprocess financial data, resulting in a significant improvement in the performance of models. However, manual feature selection methods are often inefficient and prone to errors, underscoring the need for automated, robust, and reliable approaches to improve the accuracy and accessibility of detection systems. Emphasized the importance of incorporating interpretability into financial fraud detection models, noting that the black box nature of many machine learning models creates challenges for regulatory compliance and trust. In financial fraud detection, transparency and interpretability are critical for fostering auditors' confidence in the model's predictions, particularly in high-risk scenarios. This study addresses this challenge by introducing the XGB-GP model, a hybrid approach that integrates XGBoost for future selection with genetic programming to enhance interpretability, unlike traditional black box models. XGP produces interpretable equations providing actionable insights that are accessible to both technical and non-technical users. Critic- Critique the over-reliance on traditional financial ratios, advocating for the integration of advanced analytical techniques and non-financial indicators to strengthen fraud detection frameworks. Previous research indicates that traditional methods for selecting fraud detection features often rely on manual judgment and statistical approach. While these methods can detect anomalies to some extent, they struggle to capture complex patterns and adapt to evolving fraud tactics. In this study, the point visceral correlation method is first employed to identify features with linear relationships to financial fraud, ensuring that each select ratio is economically significant. The XGBoost model is then used to automatically select the most important features utilizing the gain metric to identify features with complete nonlinear correlation to fraud. To further investigate the potential relationships between financial characteristics and fraudulent activities. This study integrates both traditional financial indicators and generate financial ratios into the screening model for a comprehensive analysis. This approach facilitates the identification of novel key indicators for fraud detection, enabling real-time updates to the model and improving its ability to effectively capture fraudulent activities. Through a joint analysis of financial and non-financial ratios using machine learning, the model identified key indicators of financial fraud, including five financial ratios such as return on equity, current ratio, and the newly introduced total liabilities to operating cost ratio. Notably, this study highlights the importance of the total liabilities to operating cost ratio, a feature often overlooked in previous research, but which has proven to be a significant indicator for fraud detection. Rigorous data preprocessing, including the removal of gray samples and adenosine-based oversampling, ensures a balanced database, thereby enhancing both model robustness and performance. Furthermore, this study employed machine learning to develop a detection method represented in the form of the mathematical equation. This equation-based approach enhances the model interpretability and user-friendliness, enabling stakeholders to better comprehend fraud dynamics and implement more effective mitigation strategies. It lays the groundwork for transparent, robust, and efficient financial fraud detection system. Data and methodology. Data. Financial fraud samples were sourced from the financial annual reports and violation records in the CSMAR database, categorizes corporate violation disclosed by the CSRC and other regulatory bodies. To ensure data consistency, only samples from post 2000 were included as pre-2000 data were incomplete and subject to different policies. This study focuses on cases up to 2020, excluding the financial industry due to its distinct reporting standards to ensure consistency and comparability. Seven categories of non-compliant records were carefully selected to represent from samples: fabricate profits, fabricate assets, false records, delayed disclosure, major omissions, inaccurate disclosure, and fraudulent EPO. Non-fraud samples were rigorously filtered by excluding companies with any non-compliant records, flagged audit reports, or STST designations. Each year of company behavior was rated as an independent sample, resulting in 5,732 fraud samples and 33,198 non-fraud samples. The samples underwent multiple pre-processing steps to ensure data quality and model reliability. First, gray samples representing potential undetected fraudulent cases were excluded excluded using Benford law and the isolation forest method to enhance data integrity. Missing values were addressed by removing samples with missing key according variables and inputting general missing data using the KNN imputer function. Next, a unified normalization process was applied. Robust standardization was used to reduce the influence of outliers, followed by min-max scaling to re-escalate the data into a suitable range. For model training, the dataset was subsequently divided using fivefold cross-validation, and the ADASI method was employed to balance the training set with 1-to-1 ratio of fraudulent to non-fraudulent samples. These steps collectively enhance the model's performance and robustness. The sample distribution for this study is present in Table 2. Indicator system. As stated in Zhang et al. 2020, identifying fraudulent companies requires selecting indicators that encompass both financial and non-financial risk factors. Therefore, we follow the same process. Financial indicators. The detection of abnormal financial ratio is a critical approach for identifying financial fraud. Unlike previous methods or approach emphasis financial indicators derived from the entire set of data in the balance sheet, income statement, and cash flow as statement. All financial ratios generated from these statements are screened and represented as a vector, where each financial ratio corresponds to a specific eigenvalue coordinate. Due to the large volume of financial statement data, the number of generated financial ratios can reach into the thousands. To mitigate the risk of model overfitting, we conduct preliminary screen of these variables. The procedure is as follows. 1. Financial items with missing values exceeding 0.7 are excluded. 2. Duplicate financial items appearing in multiple tables are removed, retaining only one instance. 3. Financial ratios are calculated using pairs of remaining items from the three tables, with the item showing the higher average value serving as denominator. Ratios are considered missing if the denominator is 0. 4. Ratios with missing values exceeding 0.7 are excluded except for essential ratios such as net profit margin, sales growth rate, return on assets, current ratio, quick ratio, debt to asset ratio, accounts receivable turnover ratio, inventory turnover ratio, operating cash flow ratio, and equity multiplier. 5. The point B serial correlation algorithm is then applied to calculate the correlation between each financial ratio and the occurrence of financial fraud. The top 500 financial ratios exhibiting the strongest correlation are selected for further analysis. Through the above steps, 500 new financial indicators were selected as input for the XGB-GP model. Non-financial indicators. The non-financial indicators data used in this study were obtained from the CNRDS and CSMAR database. As shown in Table 3, a total of 19 non-financial indicators were selected, primarily focusing on information related to internal executives, management compensation, and shareholder ownership ratios. Specifically, internal executive information and management compensation reflect the motivation and ethical standards of the management team, while the shareholding ratio provides insights into the company's governance structure and equity distribution. The financial and non-financial indicators collectively constitute the comprehensive feature set for this study. Methodology. The extreme gradient boosted genetic programming XGBGP model constructed in this paper is a hybrid approach combining extreme gradient boosting and genetic programming for financial fraud detection, as illustrated in Figure 1. This methodology employs XGBoost for feature selection followed by GP to generate a mathematical expression for predicting the target variable. XGBoost is utilized for feature selection by training a model to predict financial fraud labels and ranking features based on their importance using the gain metric. The top ranked features are then encoded to form the initial population for GP through iterative, iterative process of crossover and mutation. The population evolves to optimize the model's performance. The best performing expression from the final population is selected as the fraud detection model, providing a transparent and interpretable solution for identifying financial fraud. By integrating XGBoost efficient feature selection with the interpretability of genetic programming, the XGBGP model captures complex nonlinear relationships in a simplified equation format. This hybrid approach offers high accuracy while maintaining user friendliness for non-technical stakeholders. Empirical results. In this study, the model is based on machine learning, with financial fraud detection treated as a classification problem. The model's performance was evaluated using standard metrics, including precision, recall, accuracy, if1 score, and the area under receiver operating characteristic curve. Feature importance. Total information gain is used to measure feature importance. The resulting ranking of feature significance is presented in Figure 2. Table 4 presents the actual indicators corresponding to the significant ranking labels. The feature importance graph generated by XGBoost clearly indicates that the top 5 ratios are significantly more important than the others. Accordingly, this study selects these 5 ratios as the key features for detecting financial fraud. Return on equity, defined as net profit divided by net assets, ranks first among the top 20 significant factors in this study. ROE serves as an indicator of a company's profitability, operational efficiency, and their paying ability. Analyze various financial ratios, emphasizing that abnormal fluctuations in ROE are strongly correlated with financial fraud. From a fraud detection perspective, when ROE falls below expectation, management may resort to inflating revenue, concealing expenses, or overstating asset value to artificially improve financial performance. Such actions are often driven by motives such as career advancement, higher compensation, or the desire to sustain stock prices. The current ratio, defined as current assets divided by current liabilities, is a key indicator of company short-term solvency. A higher CR suggests robust liquidity, while lower CR signals weaker solvency. Companies may manipulate this ratio to misrepresent their financial health. Examining the motivations and methods of earnings management, noting that management may adjust financial indicators such as the current ratio to deceive investors. Inflating the CR can attract investment or loans, while artificially lowering it might conceal liabilities. Abnormal CR values should serve as red flags for auditors and stakeholders, signaling the need for further scrutiny and investigation. The ratio of total liabilities to operating costs through unconventional ranks third in significance in this study, identified by the model for its exceptional predictive power. This new indicator is crucial for assessing a company's financial leverage and debt repayment capacity. A higher ratio indicates greater debt burden, weaker financial health, whereas a lower ratio suggests healthier finances and more efficient resource allocation. From a fraud detection standpoint, companies with lower debt and higher operation costs might appear more attractive to investors, creating an incentive to manipulate this ratio. This indicator provides insights into a company's debt management that may not be captured by traditional ratios like ROA or CR. This proportionate ratio of debt to operating costs could signal potential risks such as profit manipulation or cash flow distortion. For instance, companies might overstate revenue or underreport expenses to mask financial instability. Monitoring this ratio can aid in the early in identification of such fraudulent activities. This finding underscored the importance of advanced detection techniques in addressing the companies of fraud and mitigating financial risk. The ratio of operating cash flow to net profit is a key indicator of earnings quality. A higher ratio suggests that profits are well supported by cash flow, while a consistently low ratio, particularly below 1, may signal profit inflation of difficulties in receivables collection. Companies may manipulate this ratio by employing accounting techniques such as prematurely recognizing revenue or deferring the recognition of expenses to artificially inflate profits. Such manipulation, as observed in the 2024 Chambers case, were driven by executive bonuses tied to performance measures like free cash flow. 5. The equity multiplier. Total assets, shareholders' equity, measures a company capital structure and financial leverage, with higher values indicating greater reliance and debt financing and increased financial risk. Examine the relation between corporate governance and earnings management, identifying the equity multiplier as a key indicator of financial leverage, significantly linked to earnings manipulation. Their study found that firms with higher leverage are more likely to face debt repayment pressures, which can motivate management to adopt earning management strategies to enhance financial performance and conceal the true financial condition. No financial indicators. At the same time, we found that no financial indicators, such as the shareholding ratio of the top 10 shareholders, have some impact on detecting financial fraud, but their significance is relatively less pronounced. Consequently, in our approach, which priorities is of use, these indicators are excluded from the GP process. However, incorporating such indicators may still offer value in traditional machine learning models that focus on improving prediction accuracy. Model evolution using genetic program. Splitted expression for financial fraud detection. Through parameter tuning and model evolution, the GP algorithm constructs a splitted financial fraud detection model represented as the following expressions. Um, since there are two possible outcomes for the fraud detection task, positive, negative, It is necessary to define a boundary for I in equation 1. Initial tests reveal that a smaller thres- threshold value generally yields better results. In this study, a threshold of 1 is chosen. Consequently, if I is greater than or equal to 1, it suggests an anomaly in the financial data, which may be indicative of potential fraud. Discussions. This section aims to interpret and analyze the equation evolved by the XGBGP model from an economy perspective. The equation consists of three components, each of which will be discussed separately. 1. X1 for X3, this term represents the product of return of equity and the liabilities to operating cost ratio. A high value of X1 for X3 may suggest that a company appears to exhibit strong profitability despite carrying a substantial amount of debt. This combination is commonly observed in fraudulent cases, where companies manipulate financial data by inflating profits or using excessive debt to conceal underlying financial weakness. 2. X4 5 4 X4. This term highlights the significance of operating cash flow to net profit ratio. A low value of X4 signals poor earnings quality, suggesting that reported profit may be the result of inflated earnings or non-recurring revenue streams. Such a situation can serve as a warning sign of potential financial manipulation. 3. This term is more complex and requires breakdown into several components. For the expression x1 minus x5, if the return of equity x1 exceeds the equity multiplied x5, it may indicate that the company is showing high profitability relatively to its asset base. A common sign of fraudulent activity, the term x2 for x3 for x5 minus 1 incorporates the current ratio x2, the liabilities to operating cost ratio x3, and the equity multiplier x5. A high value for this expression may suggest that the company is overly reliant on debt. In fraudulent scenarios, companies might inflate current assets or underreport the abilities to present a more favorable financial position for the distorting the true financial health. Fraudulent companies often manipulate financial indicators by inflating profits, affecting X1, overstating assets, affecting X2 and X5, or concealing liabilities, affecting X3, to present a mislead, misleadingly favor- favorable financial picture. In the equation, high values of x1 for x3 and low values of x4 may indicate potential fraud. The negative term minus x5 for x1 minus x5 for x2 for x3 for x5 minus 1 highlights discrepancies between profitability, asset liability ratios, and cash flow quality, which can signal fraudulent activity. This equation aims to detect such a fraud by identifying abnormalities in the relationship between total asset liabilities, the current ratio, and cash flow. Abnormal values in the combination of x1, x2, x3, x4, and x5 may indicate inflated profits, overstate asset, or concealed liabilities. By integrating key financial indicators, the equation helps uncover financial inconsistencies, particularly between profitability, liabilities, and cash flow, making it making it a powerful tool for identifying potential financial fraud risk. Introduced Benish Benish introduced the renowned M-score model, which detects corporate earnings manipulation by analyzing key financial ratios. These ratios not only assess a company's profitability but also evaluated its liquidity, leverage, and financial stability. The indicators in the equation proposed in this study, such as the net profit to net assets ratio, current ratio, and total asset to equity ratio, closely align with the core principles of the Benish model. Both approaches aim to identify potential financial fraud. By quantifying financial anomalies, these alignment demonstrates that the equation proposed in this study is grounded in robust theoretical and empirical foundation, sharing a similar logical framework and practical significance with established detection methods in the literature. By synthesizing several key financial indicators, the detection equation evolved from the XGBGP model effectively reveals financial inconsistencies behind fraud, particularly discrepancies between profitability, liabilities, and cash flow, and can serve as a powerful tool for detecting potential financial fraud risk. Comparative experiments. In this study, M-score logistic regression, SVM, XGBoost, and RNN models were selected as comparison models. Among them, the M-score and logistic regression model represent traditional fraud detection methods based on statistical approaches, while SVM, XGBoost, and RNN model represent machine learning techniques. The SVM was chosen for its effectiveness in handling dimensional feature spaces. XGBoost, a robust gradient boosting algorithm, is particularly adept at capturing complex nonlinear relationships and serves as the primary model for feature selection in the proposed hybrid framework, making making it a key comparison model. Given the temporal nature of financial data, RNS were included for their ability to capture time-dependent patterns. In the comparative study, aside from the fixed ratios in the M-score model, the logistic regression SVM and RNN model all utilize the necessary financial ratios outlined in section 2.2. In contrast, the XGBoost model employs a feature set comprising the top 500 financial ratios selected using the point B serial correlation method, along with 16 non-financial ratios for section 2.2. The XGBGP model, on the other hand, lever leverage 5 key features selecting in section 3.1. This approach of using a smaller, more refined feature set in the XGBGP model aims to enhance detection accuracy while preserving interpretability and ease of use. The performance of each model is present in Table 5 and Figure 3. From the perspective of evaluation metrics, XGBoost outperforms all other models, further confirming its effectiveness in fraud detection and underscoring its robust feature selection capability. The XGBGP model follows closely behind XGBoost, demonstrating high precision and recall, thus validating its strong performance in detecting fraud. Other machine learning models, such as RNN SVM, show some effectiveness but do not achieve the same level of overall performance as XGBGP and XGBoost. In contrast, traditional methods such as the M-score and logistic regression models perform relatively poorly. This suggests that traditional approaches struggle to capture the complex nonlinear relationships between features and labels, rendering them less effective in identifying fraudulent activities. The advan- advantages of the XGP model are evident not only in, in its superior evaluation method but also in its simplicity and transparency. Unlike the XGBoost model, which relies on a large number of features and operates as a black box, the XGBP model achieves high performance with only 5 features and a transparent equation. This makes the XGBGP model both user-friendly and efficient. Moreover, it presents results through explicit equation, providing detailed economic interpretation of both individual features and the overall equation. This enhances the model transparency and interpretability, thereby increasing its credibility. The hybrid model developed in this study automatically selects features using machine learning techniques, minimizing manual intervention and making it highly adaptable to the era of big data. The model is capable of continuously updating its indicator and equation to respond to evolving fraud tactics, enabling enabling it to detect increasingly sophisticated fraudulent activities. Additionally, an effective data processing strategy bolsters the model training efficiency techniques such as a gray sample exclusion and data argumentation improve the model's ability to learn from fraud characteristics and strengthen its detection capabilities. By combining high precision, transparency, interpretability, ease of use, and efficiency, the XGB-GP model represents a comprehensive and robust solution for financial protection, outperforming other models. For research implication, this study introduced the XGBGP model, which demonstrates superior accuracy, precision, and interpretability financial fraud detection. Unlike traditional black box models or approach leverage XGBoost to identify key characteristic factors and construct a transparent mathematical equation using genetic programming. This makes the model more accessible, allowing users to easily understand and apply and compare it to conventional algorithms and more complex machine learning models. Our model offers distinct advantages in financial fraud detection. It is not only user-friendly for non-technical users, but also provides a clear interpretative framework, enabling companies and regulatory bodies to quickly detect and respond to fraudulent activities. The feature significance analysis in our study provides valuable insights. The total debt operating cost ratio, ranked third in importance, offers crucial information about a company's financial leverage and debt repayment capacity. This finding highlights the potential value of previously underutilized financial ratios in detecting fraud. Furthermore, it underscores the limitations of relying solely on traditional financial ratios when addressing increasingly sophisticated fraudulent activities. In a real-time financial fraud detection system, the XGBGP model supports incremental training, allowing dynamic adjustments to K-Pro indicators and the corresponding equation based on incoming data. This allows the model to update its weights and tree structure as the dataset grows, eliminating the need to retraining from scratch. Since the features input into the XGBGP model are select using the point biserial correlation method, interpretability of the updates feature is not a concern. The initial statistical filtering ensures that each feature possesses economic significance, thereby guaranteeing the interpretability of the resulting equations. Unlike traditional statistical models or machine learning-based feature selections, and equation construction methods enable to model to efficiently and accurately self-update in response to evolving data. This adaptability allows the model to thrive in big data environments and adjust to changing fraud tactics. Conclusion: financial fraud and financial risk are closely intertwined, mutually influencing each other and contributing to the risk factors of the financial market. An effective and user-friendly financial fraud detection model can enhance auditing and supervision, improve investors' ability to identify fraudulent activities, and significantly reduce the occurrence of financial fraud. In this work, we introduce the XGB-GP model, which combines XGBoost for feature selection and GP for fraud detection, or models user-friendly, design efficient, and adaptability make it highly suitable for practical application. We also emphasize the importance of true data collection and minimize the impact of false samples on the model. The validity of the model has been confirmed through empirical results. During the research, we also identified a new financial ratio with significant relevance to fraud detection. This finding highlights the complexity of detecting financial fraud and underscores that traditional financial data alone is no longer sufficient to fully uncover fraud risk. Looking ahead, fraud detection will increasingly rely on the integration of multidimensional multi-source data, allowing for the extraction of more comprehensive features from diverse information sources. Bueno, este artículo básicamente trata o este estudio trata de evaluar la efectividad de prácticamente de que hay un modelo híbrido llamado XGB-GP que sirve para la detección de fraude financiero. Entonces, lo que hicieron fue, para crear ese modelo, fusionaron XGBoost, que lo que hace es que lo que hace este modelo es interpretar la programación para generar pues como las ecuaciones y para interpretar los datos. Y está la otra parte que es la de GP, que es la parte de los datos que se toman a partir de a ver, es como si, pues como lo dicen mejor dicho, como lo dicen en el estudio, SGP es la programación genética. Y con lo que hacían con el XGBoost era como para poder clasificar las características según pues como los indicadores financieros. Y la parte de la DGP, que es la programación genética, con estos, a través pues de varios algoritmos, buscan como encontrar como la expresión matemática que pueda predecir la probabilidad pues de que pase ese fraude financiero. Obviamente ellos manejan pues como unas expresiones, unas ecuaciones pues que son las que tienen mejor rendimiento en cuanto a la medición de la población final, y se seleccionan pues como el modelo de detección del fraude. Básicamente, pues este XGBGP implica que primero tienen que utilizar el XGBoost para identificar esas características financieras más importantes para poder predecir el fraude. Y luego estas características se utilizan en un algoritmo de programación genética que es el GP para generar la ecuación matemática donde la pueden interpretar y así se puede detectar el fraude financiero. Entonces, lo que hacen con este enfoque es buscar combinar pues como una más alta precisión de los métodos de aprendizajes automáticos con la interpretabilidad de esos modelos basados básicamente en las ecuaciones. Entonces, ellos que concluyen que en el estudio de ese modelo, el cual demuestra pues como una mejor precisión o una mejor exactitud en la interpretabilidad, en la detección del fraude financiero, es gracias a la combinación de esos dos modelos. Y a diferencia de los modelos que ahí hablan también otro que se llama The Black Box o la caja negra, permite que con el modelo del que están hablando en el artículo, permite pues que los usuarios puedan comprender mucho más fácilmente y aplicarlo al modelo de detección de fraude. Entonces tiene una mayor interpretabilidad para el usuario, así el usuario no tenga mucho conocimiento y tampoco no sea muy experto. Entonces lo comparaban con ese otro tipo de modelo que se llamaba la caja negra o black box. Entonces también hablan de que en cuanto a las conclusiones, que el análisis de la importancia de esas características releva pues que es adecuado para aplicaciones prácticas debido a su diseño fácil de usar, a la eficiencia y adaptabilidad, que también se enfatiza mucho en la importancia de una recopilación de datos para poder minimizar el impacto de muestras falsas que hayan en el modelo. También destaca mucho pues que la detección del fraude financiero es demasiado compleja y que en realidad los datos financieros tradicionales por sí solos ya no son suficientes para poder descubrir completamente eh, esos riesgos de fraude. Entonces, en el futuro, la detección de fraude depende cada vez más de la integración de datos y de múltiples fuentes para poder extraer pues toda esa información que al final van a poder, con todos los datos que se toman, van a poder detectar más fácilmente eh, esos riesgos de fraude. Entonces, básicamente, ese modelo que es el XGBGP admite lo que viene siendo los ajustes dinámicos a los indicadores, que viene siendo pues la clave del fraude y obviamente pues mediante esas ecuaciones correspondientes basados en los datos que se toman sin necesidad pues de que haya un reentrenamiento completo. Entonces la interpretabilidad de las características que se actualizan se mantienen gracias a que hay un filtro estadístico inicial que asegura que la significancia económica de cada característica sea la más apta. Entonces, básicamente, y para finalizar, el estudio presenta el modelo XGBGP como una herramienta que lo que hace es detectar el fraude financiero, superando a otros modelos en términos de precisión e interpretabilidad. Y además resalta la importancia de considerar indicadores financieros menos convencionales y la necesidad de enfoques adaptativos para hacer frente pues, a la evolución de las tácticas de fraude.